Thank you very much. I'm not from Warsaw, so hopefully no rivalry with me at all. I run... I don't think they've put the slides up on the screen behind. Oh, there we go. Brilliant. Brilliant. So I run a company called Option who sell and make low overhead production profiling tools, and I'm here to talk about fantastic performance. We will see our tool in it, but it's more about the methodology and the approach and how do you identify and understand these problems. So I'm going to talk about a few different things in this talk. Firstly, I'm going to talk about what we mean by where to find performance problems. What do we actually mean by fantastic performance? What are we aiming to get here? Then I'm going to go through a few different examples of profiling some applications, and then we'll look at how those kind of profiling examples correspond to the real world, how you can actually use them on a proper production system. And we can wrap up some threads at the end. So I put this term fantastic performance in the talk title, mainly as an excuse to get a film reference in there. But what do I actually mean by fantastic performance? I mean, for me, fantastic performance is often performance that meets business objectives. It's plain and simple like that. Keeping your customers happy with responsive applications that load nice and fast. Keeping your infrastructure costs down and nice and low, especially on cloud environments where you're metered for everything you possibly do, CPU, memory, everything. And also having the ability to scale out. So it's not really about using fancy technologies, it's just about getting those core things right and meeting your business objectives. Now, when it comes to meeting those kind of business objectives in terms of performance, a lot of people will jump into a new architectural trend and tell you all sorts of things. You need to go reactive. You need to go microservices. You need to go, you need to go and do all sorts of crazy things. But this isn't really a talk about architecture. I'm not here to say there's one way to write applications and that's the only way or the only right way. That's not to say any of these ideas are bad ideas, but they're all appropriate in some context or some business situation. What I'm here to talk about is how we can measure and understand these things. That's to say that achieving fantastic performance isn't something that you need some kind of magic one trick in order to achieve. It's something that you can think about more scientifically, more methodically. Hardware these days is incredibly cheap and incredibly fast compared to where we were 10, 20, 30 plus years ago. Amazingly good. All we need to do as software developers is try and remove the sources of bottlenecks and inefficiencies within our software stack, and we can often get this hardware to absolutely go like a rocket. Okay, so let's run through a few examples of what I mean by finding performance problems using profilers. So, firstly, what do profilers do? For me, profilers are about finding what the main consumer of a resource is, a computational resource in your application. So that could be CPU time, as in the amount of time you spend on CPU actually executing instructions, actually retiring instructions. It could be wall clock time, so the beginning and end of operations. That's a time that might be important to your users, their time. It could be the amount of memory that you're using. One way of phrasing this is that profilers are the who ate all the pies of performance engineering, right? Or maybe to localize that, the who ate all the pierogi. They're also an opportunity for us to challenge our mental model with some data. So we all have an idea on our own minds as to how our application performs in production. And sometimes those ideas can be quite wrong. You can not realize certain things about the way your application is performing. Similar to the way that debuggers let you understand when things aren't matching your model in terms of an execution perspective. A profile is the first thing we should look at when trying to understand performance problems? I don't think so. I think the first thing to look at is raw CPU metrics. They're really, really helpful for narrowing down different problems. If you even simple tools like VMstat, though it's not really, I'm not saying use VMstat, lots of people have fantastic monitoring and information available about those CPU operations these days, but even just simple tools like VMstat can reveal a lot of information about the way your system is behaving. Just take those 5 little metrics on the end. User time, that's the amount of time that is being spent in user space in your system. System time, that's the amount of time, CPU time that's being spent executing code in the kernel. So that could often be associated with doing a lot of network traffic, a lot of disk I/O, things like that. Idle, time when your CPU could be used, but you're paying for it and not making anything of it. Wait, that's time when it's sitting around waiting, blocking on an operation that's doing some I/O. And ST there is steal time. So that's something that you might well see on AWS nodes a lot, especially the smaller AWS nodes. That means you're running in a VM, and another VM on the same hardware is stealing your CPU away from you. So let's, so the examples I'm going to show here are also all available on GitHub. So I'll put these slides up on SlideShare after the talk. You can go take a look at them. You can download that code and play around with it yourself. It's just a very, very simple toy demo project with a few obvious problems in that we can work our way through. So let's take a look at a kind of CPU bottleneck type problem. So I'm going to start up a system here that's just running a little web service locally. And that is going to rebuild itself and start running in the background. It's just a basic drop wizard service. And what I've done here is I have imported the house price data from like a whole month's worth of house price transactions in the UK. And I've got a little web service that will let you search through those transactions. So for example, here I have looked up and got the house price transactions related to Cardiff in Wales, where I was born. And as you can see, some of the house prices are very cheap, £266, and the most expensive ones are very expensive, £29 million. And I've just pretty printed this JSON. So this gives you a load of data about this service. Now, if I just run this house search, I'm going to hit this endpoint repeatedly, and I'm only going to hit it with 100 requests here, so we aren't waiting all day for this operation to complete. But we'll see it takes quite a while to repeatedly do those searches in our system. We want to see why it's slow and how we can improve them. What this housesearch.sh script is doing under the hood is just running the Apache benchmarking suite. So that's running a bunch of requests against the system, and we can see that our 50th percentile is about 800 milliseconds for a request, and our worst case is a couple of seconds. So let's just flip over to a profiler view here, and let's go into the future at some point and see what our Devoxx demo was doing during that time period. So this is a flame graph view of what your application is doing. Who's familiar with flame graphs or has seen them before? A few people, good. Not the majority, that's okay. We're going to talk a little bit about what flame graphs are. So flame graphs are a way of visualizing what's going on inside your application in performance terms. So each box inside a flame graph corresponds to a single method in your application, and how wide that box is corresponds to how much time that method or its callees, its children, took up. So if you look at the shape of a flame graph and you see these kind of fat wide boxes like this, you can kind of see that those methods weren't taking up much time themselves, but because they were very wide, something that they called at the bottom of the stack ended up taking up lots of time. And what you'll often see, if I just zoom in a bit so you can actually read some names here, at the top of JVM stack traces, you get Java lang thread, so that's what we might expect to see at the top. And as we go down, we might go through some JVM code, some framework code, and along here, we get into some of our demo code. So we hit that house resource.sales search method, which was the kind of HTTP entry point that we were hitting with that benchmark script. And that looked up the sales query.search method. And then there are a couple of methods here, get sales data and read sales data, that corresponded to the bulk of time inside the application there. And underneath them, we can see that they were reading a CSV file, we were parsing some dates. It's kind of weird. It's not actually spending the time searching, it's spending time doing CSV processing. So let's have a quick look at what that class actually does here. So this is the sales data .get sales data method. Let's just read through this code and see what it's doing. We've got a sales data field that we might expect get sales data to return, but it lazily initializes that field, right? So it checks if it's null, we'll read the sales data, otherwise just return it. But we're never actually assigning any of that data to the sales data field. Okay, so let's fix that up. Also, this is a field here, and if we just left it as it was, that would be a race condition. So I'm going to throw in a quick static keyword there. So that static keyword would make sure that we don't have multiple threads initializing or trying to read that data at the same time. It might be a bit of a benign race, but we don't really want it anyway. Okay, so we've restarted. Let's see what happens if we run a request again. So we've done another 100 requests here. I mean, we might want to do a few more, to be frank, just to see what's going on here. And because we can see as well, just from how fast it completed when running the command line script, it's a lot faster, but some of the data here is telling us things more interesting. We still have a bit of a bad tail latency situation of 1,000 milliseconds, but we've also got much reduced time for our average response time. So what this table of data here tells you is half the requests took 67 milliseconds or less. All of them took 1 second or less. And that was massively improved from what we had beforehand. So let's go back here to our profiling view and change things up. I want to see what this latest run of data would tell us. And let's scroll down to the bottom and see what it's doing now. So if we look back at our sales query search method that we had beforehand, we don't have any of that CSV reading nonsense in there anymore. We've removed that source of bottlenecks. But we have a different operation that's going on here. We can see we've got Java util stream reference pipeline.collect in our stack trace, and that's very common if you have a profile Java streams code, because it's always the terminal operation that actually kicks off the execution of a stream pipeline. So you'll often see things go through collect. And then we've got a bit of stream code there, but it's not really the stream framework that's taking the time up here. It's our methods that are being called back here. This search lambda and this contains ignore case method. So what's contains ignore case doing? Mostly, it's calling to uppercase on a string. So let's see what that would be doing. Contains ignore case. So this is a really dumb way of implementing a contains ignore case method, right? We take a string, we uppercase it, check it contains another uppercase string. There's a bunch of frameworks and libraries that we can do in order to solve problems like this. So Apache Commons collection util has a string utils class, which has a nice contains ignore case on it, and we can just pass the field and the query string in there. Okay. So if I rerun that script, having made that change, and boot our application back up, and we'll rerun our benchmark against it. Okay. And we would hope to see things go a little bit faster this time around. And we can see we've gone down to about 50 milliseconds from 67 beforehand. We've still got a bit of an outlier, so there's still some stuff going along there. Okay, what does our profiler tell us that we're doing this time around? Well, we are still in contains ignore case, and we're still in the string utils.contains ignore case. So ultimately, the bottleneck is still comparing those strings inside our application. We found a more efficient way of doing it, and we know it's more efficient because the total time of the operation has reduced, but it's still sitting there taking up plenty of time in our application. So what I'm actually going to do in this case is I'm going to use a bit of domain knowledge. Now, it turns out that this contains ignore case is a very, very conservative way of making this comparison. Because if you actually look at the data in the CSV file, you'll find that all these names are uppercased for you anyway. So thank you very much, UK government, finally doing something useful. So we can actually, knowing that they're uppercase, just straight off make a comparison between the uppercase of the query string and the field. So that's an example of a situation where our profiler has told us that the bottlenecks in this part of our application, we still need to focus on that hotspot, that problem in particular, but we've been able to bring a little bit of domain knowledge into this situation and see what's going on there. And if I rerun this house search this time round, we can see that we are below 20 milliseconds for our 50th percentile. So a lot of our customers would be much happier at that point in time. But profiling to find CPU bottlenecks is probably the most well-known form of profiling Java JVM applications, or applications in general. When you've got a hot CPU-bound operation, profiles are something that people often reach to. But what's more interesting is that you can often find non-CPU-bound bottlenecks also using profilers. So those are blocking bottlenecks. Now, in this next example, I've got a demo application. This demo application it's the same drop wizard application. It's got a few bits and bobs in there. Everyone else is doing microservices. This is a bit of a macro service. All the demo code in one big application. And it's talking to this legacy bank service. And it's actually got an endpoint that we can hit that will take data and take the customer's balance from a legacy bank service that I'm just running in the background on my application, and update and store that data within the bank account and bank service of our drop wizard app. Okay, so let's start that up in the background. And in this application, I'm going to run a slightly different script here called merge accounts. Now, what merge accounts does is it runs a bunch of different benchmarks in parallel. So it takes several different users and hits those HTTP endpoints to merge their bank accounts in. It does it repeatedly in this case, just because we want to see some kind of benchmarking number out of it at the end. And these operations take quite a long time, so this whole merge account script takes a little bit of time to run. 29 seconds was our first effort. Okay, so let's pop back to the profiler and see what it tells us for this application. Well, if I run a bit of profiling, we can see we get a very different, just without looking at what any of those methods are, we get a very different kind of profile coming out of this application. No real clear hotspot, no real clear user of CPU, nothing that obviously draws your attention to. But something that would perhaps draw your attention is the top method of 55% of our application, which isn't javalang thread.run, as we'd expect inside a regular thread pool doing kind of business operations. It's the hello world application.main method. It's the startup method. So why is so much of that CPU time being spent there? Well, the reality is that this is not a CPU-bound operation. This is an operation, if we looked at the CPU metrics, that would say most of the time your system's sitting around not doing very much. It's just, what is it doing? Well, that's what wall clock profiling is here to tell us. So wall clock profiling, which is this alternative view I've just switched to here, is a way of measuring what your application operations are doing from the beginning to the end. So they're good for finding blocking type problems, things to do with locks waiting around, but they may not necessarily be locks in your application. So let's see, we get, again, a very similar kind of dominant consumer type flame graph where it's mostly one operation going on. And where you see these flame graphs narrow in, that's where you see the self-time in these kind of operations. So let's take a little look down here. We've got a method here called merge balance from legacy bank account. We actually have some of it over here because you've got different synthetic access methods that the reflection has generated from us. And we can see that both of these points are the points where our flame graphs narrow in. That's where you kind of see on flame graphs the hotspot starting to appear. And the interesting thing here is, even though there's a method below it, legacy bank proxy.get bank balance, that's the method that actually goes off and talks to that legacy bank account, it's not the thing that's taking up most of our wall clock time. It's the self-time of merge balance from legacy bank account as a method. So let's go off and take a look at our bank class. Now, we can see that this method actually isn't doing very much. It's not doing any arithmetic. It's not doing anything computational. It's just calling other methods. We know those other methods aren't the real bottleneck because we'd see them in our profile otherwise. So what's it actually doing in itself? Well, it's got this big synchronized block, and it's got a big transfer lock at the top. So what it's doing is performing all these balance update operations under a global lock. Now, I have a convenient getLock method here. And what that will do is it gives you a lock for manipulating the person's bank balance that's based upon the ID of the customer in question. There are different locking strategies that you can use in these situations. Things like stripe locks often come into account, being quite useful in these situations where you can get an NM mapping of locks to customer IDs, things like that. Either way, we would expect this operation to speed up quite a lot when we try and rerun those merge accounts operations. And we're down to 8 seconds here, so not quite a fourfold speed up, but pretty good. Now let's take another quick look at our profile. This time around, we can see that there is no clear and obvious point where our flame graph narrows down. It kind of just gets to the bottom of the flame graph, and when you get to the bottom of the flame graph, you see socket input stream.socket read 0, and this other part of the flame graph here is also socket read 0 there. So what are those methods doing? Well, this is often quite common if you look at a wall clock time-based profiling view of an application. So if your system is talking to another system over a network, if it's a microservice-based operation, if it uses a database and it's talking to a database over even on the same host, you'll often be calling a socket read 0. When you see wall clock time that's spending a lot of time in socket read 0, it is waiting blocked on an external system. So how do we know what external system to look for? Well, we can just see straight up the stack trace here from where in our application code that code is being called and what it's doing. So here we've got our legacy bank proxy.get bank balance method, and that is calling some code in the Apache Fluent HTTP client that's making an HTTP GET request, and then that's what ends up calling our socket.read0. So we're making a HTTP GET request to this external service. Now, that means you need to reapply that entire process of optimization on that other legacy service. Maybe you need to bribe the team that manages that external service with chocolates, hugs, whatever you need to do to get the operation done. Now here I'm going to cheat a little bit because it's a demo and a talk. And what I'm going to just do is flip that external service to be much faster and rerun my merge account script, and that's also way faster, just half a second. So bottleneck removed entirely there. But the key point here is not that you can just flip a number in a demo script. It's the fact we can go through this process, find that dominant consumer for blocking problems as well, and resolve them. Okay. Cool. Now, I've given a few examples there. They're kind of simple examples that I can run on my laptop in a demo in 30 minutes at a conference. But in the real world, things are rarely that clear-cut or simple or nice, right? There's often, military figures have this concept of fog of war, and you often get in that kind of fog of war situation when you're looking at a production system, right? There's a lot of noise, a lot of things in the way. So how do we take that same basic methodology and approach and solve the more real-world situations? So I'm going to go through a few different problems you might encounter and how we can solve those. The first problem you might hit is your unrealistic workload. So in that benchmark, I say it's a benchmark. I treated that a little bit fluidly. It's not the world's best performance test. If you really want to do performance testing well on a production system, it's really, really hard. You've got to make sure that the request rates that are being generated by your load test harness are exactly the same as your production system. You need to make sure that you're hitting the same distribution of things like user IDs and data. Otherwise, caching can often give you much more optimistic numbers in a performance test than a real world. You need to make sure that the hardware that you're running your benchmark and suite on is the same as you use in production. Otherwise, it can tell you, ooh, you've got a CPU-bound problem on a laptop with a few cores, and in a production system on a 30 or 60-core machine, you end up with lots of lock contention problems because you've got lots more cores to use. So getting that performance testing right is really challenging, and getting it wrong leaves you with this unrealistic workload that can possibly give you the wrong answer. So that can mean either A, you waste a lot of time optimizing the wrong benchmark, or B, you're unable to solve that problem rapidly and you annoy your customers or burn through too much money on infrastructure or whatever the underlying problem is. The solution I suggest with that kind of thing is don't worry about performance testing. That's not a 100% rule. I don't think anything is a 100% rule. But in practice, for a lot of development teams, the effort to try and get performance testing and load testing really accurate on your system is so high, it's so difficult, it's probably not worth your time doing it from a cost-benefit perspective. The best thing to do is to actually measure what your production system is doing itself. So that gives you a real production system. You don't have to worry about the hardware being different. It gives you the real production data, and it gives you the real production workload. We had customers at Option who have ordered things in their code, assuming certain things or measuring things in their development environment. They've used the exact same hardware. For example, on AWS, they've replicated the load correctly, but simply by having different sizes of data in their production system and things like that, it's caused them a big difference in outcome of performance. But in order to measure those things in production, you need to have a really low overhead profiler. Now, aside from Option, which is a low overhead continuous profiler, there's also a few open source tools you can use in order to get going with this kind of stuff. Async profiler, honest profiler, and perf with the JVM perf mapper agent. are all GitHub open source projects that are very, very low overhead. They can all be configured to be low enough overhead for production usage. There's also flight recorder and mission control, which is now open source if you're using Java 11 or later. And there's also good old Solaris Studio, which is an excellent profiling tool as well. Don't be fooled by the name. It actually works better on Linux than Solaris. Problem number 2 you might encounter applying these ideas in the real world: intermittent issues. So a lot of performance problems aren't really continuous, always going on issues, right? They're triggered by bursts of activity. So for example, if you ever look at financial markets, capital markets, once a month the US government releases its non-farm payroll data, their big economic stats dump for the month. And the moment that data is released, everything goes crazy. Trading volumes go through the roof. Lots of people do different things. If you look at, say, gambling markets in the UK, when the Cheltenham races, the spring races are going on, loads of activity, lots of people betting, hopefully not that much money, maybe a lot of money on different horse racing activities. And often, people like e-commerce sites may well do one-off sales, Christmas rush, sort of things like that. Things where you get an intermittent issue at a given point in time. It might also be the case that these intermittent issues aren't something that coordinate very well with where your developer team is. If the issue happens at 1 a.m. at night, and your tier 1 operations support fixes the problem just by restarting a server, perhaps, then you may not have time to gather the data in order to solve that problem. So how do we solve intermittent issues? The solution to that problem in terms of how you apply profiling for that is continuous profiling. So always profiling your production system, keeping that historical data. It gives you so much ability to compare and see what's going on. So you can see what happened during the time period that you had a problem compared to the last time you had that time period. You can see what it looks like compared to a regular day, and you don't need to worry about trying to hook up or configure these kind of profiling tools when you've got an outage and when your number 1 responsibility is just get stuff working again, get the customers happy. Problem number 3, infrequently used code. So traditionally when you see people talk about profiling, they do the kind of thing that I did earlier in this talk. You have a benchmark, the benchmark does some load on some system, and you see what the implication of that load is. Now production systems don't necessarily have their most important or most critical parts of the system as being something that's always under load. Just take the example of a sign-up process. If your business is trying to acquire customers, maybe you're paying some good old advertising spend to get people to hit that sign-up process or part of your website. Maybe you're doing lots of marketing, whatever. People hit that sign-up process, and you want to onboard them with as good a conversion ratio as possible, right? You don't want to be wasting your money on getting customers to hit that sign-up process, only for them to not bother signing up because it's a slow process or the sign-up system's down or things like that. A lot of money is lost by companies on that kind of thing. But the sign-up process of your website is really, really unlikely to ever be the dominant workload, right? You're much more likely to have people actually using the system rather than signing up to the system as the real source of work. So, how do we deal with problems like that kind of traditional benchmark plus profile doesn't work? And the solution to that kind of thing is querying, slicing, dicing of that profiling data. So being able to take the profiling data that you've gathered from your production system and being able to do things like filter on methods that are in that production system is incredibly useful. It means you can do things like narrow down to endpoints that deal with just sign-ups or logins or a few one-off critical parts and see what actually is taking the time on those portions of the application. Now, another problem that infrequently used code often results in when you're looking at profiling is not having enough data points in order to understand the profile. Profiling is a sampling-based process. You're seeing what the application is doing at certain points in time. So if you don't have enough samples, you're not going to get a statistically relevant picture or an accurate picture of what's going on. But if you're continuously profiling, you often have enough data over a longer time period, even when you're looking at more infrequently used parts. And the other problem with profilers, in terms of how we can actually use them in real production systems, which is where we kind of want to use them, is the problem of access and the problem of scale. Now, who here has access to the production system that their company runs, like can SSH into the box and add stuff? Some people, I'd say that's like 10%, maybe at most. Not that many. In some organizations and some industries, you actually have legal barriers, Chinese walls between different parts of the organization. Often barriers that stop you, especially in things like finance, investment banking, that stop you from having people who write code to run on a production system, also being the people who operate that production system as well. So there's a real access barrier there that would stop you from using most traditional kind of hook it up on the fly type profilers. And then there's the scale issue. You know, lots of people have production systems that have 10, 50, 100, 1,000, you name it, a lot of servers there, and trying to connect into one or two of those systems in order to measure what's going on. It's a real, not a practical solution to that kind of problem. So the solution to those kind of problems is decoupling the profiling management from the visualization and the user interactive parts of your profiling system. Have some JVM agents that gather data, have an aggregation service, have some reports on the web that you can look at that keeps that aggregation service, and have that aggregation service be pre-connected to a load of machines. At Opsian, we do this kind of stuff, but it's not like we're the only organization who's come up with that idea. Google, a number of years ago, released a paper called Google-wide profiling, where they talked quite extensively about what they were doing with those kind of ideas, how they were aggregating their profiling data and keeping those kind of always-on continuous profiling solutions. Cool. So let's wrap up this talk and conclude with what we've said. Firstly, I think it would be remiss of me to talk about low overhead profilers without giving thanks to a lot of people who've done fantastic work developing really low overhead tooling on the JVM. So people like Brendan Gregg, who came up with flame graphs as an idea, Andre Pangin for Async Profiler, Jeremy Manson, Johannes Rudolph, Nitsa Mokart, and obviously the Mission Control and Solaris Studio teams. Lots of great work done on low overhead profiling on the JVM. These things really differentiate in terms of the amount of overhead and the practicality of usage in a production system compared to tools like JVisual VM that are just so hard to use in that environment just due to the overhead. We talked at the beginning why we wanted to have these kind of, why we wanted to investigate performance problems and what fantastic performance meant. It meant meeting our business benefits. Responsive, reliable websites that don't go down under load, that gives us happy users. Cheaper infrastructure gives us happy accountants. And scalability, happier VCs are always looking for scale or senior management. I talked a bit in detail about how you could apply profiling to your application. So looking at different CPU times to see where the bottleneck was, what was really going on with your system. Were you using a lot of CPU up, or were you waiting on external systems? And then we can start thinking about what kind of profiling data we can capture from that system. Is it CPU time, which we'd use when we're CPU bottlenecked? Or is it wall clock time-based information to use when you're not using much CPU up at all? Flame graphs are a really cool way of visualizing profiling data. They tell us about what's calling what's code, what code is calling what other code. They're a nice visualization. And if you want to use flame graphs, the real way of understanding them is looking for where they narrow in and looking for the shape of the flame graph. Often you want to have a look if you've got very fat tails on your flame graph, and especially if they're things like socket read 0, or looking at things like reading from a file input stream. then those are things like talking to external services, reading data from files. So that's especially useful in a wall clock sense to understand where those things are coming from. But usually just by looking back up the flame graph, you can see where in your application this operation was triggered, and thus what you were doing, what service you were talking to. What we talked about today is a data-driven optimization of the dominant consumer. So that's a bit of a fancy term or a bit of a fancy phrase for saying, find the biggest bottleneck that's relevant to your operation, optimize that bottleneck, iterate and repeat, and do it scientifically. Rerun those benchmarks and see what's going on, and you can solve those problems really easily. I guess what I really wanted to say in this talk, or the kind of one-sentence summary is, solving performance problems isn't really like taming some magical wild beast or anything like that. It's a scientific process. We can do it with a bit of methodology, a bit of measurement tools, and a little bit of rigor. And often people think about using profilers in a development environment, which is fine, that's totally cool. But actually, they can also be used in production. And that's not only where you can use them, but it's often where you can find the best and most valuable usage out of them. Thank you very much. That's the end of the talk. If anyone has any questions, I've got about 8 or 9 minutes for them. Has anyone got any questions? Hands up. Do you want to shout out? Okay. This gent's coming around with a mic.
There is actually a problem number 6. As soon as you plug in the profiler on the production, there is a security department pops up and goes mad because you're deploying the tool to mess up with memory, with thread scheduling, with everything. Do you know the solution for that problem? It's actually
yeah, you need to have a talk with your security department. We've had discussions with a number of security departments at customers, and either you need to have an aggregation service that can run on-premise like we do, or you need to have a way of convincing them that storing that profiling data is somewhere that's auditably secure. Any other questions?
Sorry. Thanks for your presentation. Back in the old days, Java 8 required some special instrumentation to enable recording data for frame cache, so I'm referring to preserve frame pointers flag. Is it still required, relevant, any such specific instrumentation to acquire data in the way that it's consumable to produce frame graphs?
So the question was, you used to need to enable frame pointers in Java 8 in order to measure profiling data. So I believe that's still the case if you want to use the Java perf mapper agent, which is what was using that frame pointer information in order to get perf to extract that information. There are other methods you can use for profiling that data, such as async get call trace, which is also very low overhead and doesn't have the frame pointer requirement as well, and also will profile data that's not been JIT compiled for some reason as well. I think there was a guy in the front row here.
Could you show getLock method body?
Sorry?
GetLock method body. Body of getLock method from this listing which you had.
Could I talk about deadlocks?
Yes.
Yes. I can talk about deadlocks. I mean, if you profile an application, you will often see where deadlocks are happening inside your application. Because, well, you'll see if you look at, say, a wall clock-based profiling view, because you'll see a certain number of your threads waiting on a certain point on a certain lock, and another part of your threads also waiting on a certain point on a certain lock. So you'll see that deadly embrace. But you would really need to be looking at like a wall clock-based profiling view in order to see a deadlock in a production system. Because on a CPU time-based view, your system will be deadlocked. It won't be using any CPU up, so it won't be very visible at all. Were there any other questions? No? Okay, well, I'll be here for a little bit afterwards anyway, so feel free to come and talk to me. Thank you very much.